Hello everyone. So, what do you see on the screen? There are some numbers. The numbers are 1, 1, 2, 3, 5, and it goes on like this. So, do you recognize any pattern within these numbers? Apparently, they may seem random, but if you look closely, you can identify a pattern hidden inside the numbers. Like if you add 1 and 1, you will get 2. If you add 2 and 1, you will get 3. And like this, it goes on. So, this is called a Fibonacci sequence, and many of you must have heard about it. So, what is the importance of this Fibonacci sequence? So, in nature, many things that apparently seem random follows this Fibonacci sequence, like the number of petals in a flower, the branching pattern of a tree, or musics. They follow this Fibonacci sequence. So in crystallography, what we do is to identify these patterns, to classify them into different groups, and to identify the elements that make up these patterns. So why this pattern recognition is so important for crystallographic purposes? So to understand that, we must understand the definition of mineral first. So for a material to be classified as a mineral, there are 5 basic requirements that must be fulfilled. These are: the mineral must be naturally occurring inorganic solid, it must have a definite chemical composition, and most importantly, it must have an ordered internal structure. So in crystallography, we are concerned about this ordered internal structure. We will study about it. So this is a transmission electron microscope picture of cordierite. So any crystal is made up of atoms that are stacked up in a particular pattern. In this cordierite crystal, these white spots are atoms. So these atoms are stacked up in a pattern and form the crystal. In this picture, the hexagonal pattern is clearly visible. So moving on, to study crystallography, we must have some basic ideas about these definitions. So remember, these are just definitions. You don't have to worry about it. You just have to understand the concept, and these definitions will come automatically. So motif. A motif is a distinctive and recurring form or shape in a design that can be an atom, molecule, or group of atoms in a chemical structure. So in a design, a design is made up of certain element which is repeated after certain intervals. So this element is called a motif. So next comes lattice. A lattice is a network or array composed of single motif which has been translated and repeated at fixed intervals throughout space. So if we take a motif and we repeat it at certain intervals to fill up a space, we will construct a lattice. And one thing you have to keep in mind, that in a lattice, the environment around each motif is exactly the same. Next comes the unit cell. So the unit cell is the smallest unit of a lattice that can be repeated in 3 dimensions to construct the entire lattice. So to think of an example, we can think of a building which is made up of exactly same looking rooms, and these rooms are constructed out of bricks. So these bricks can be represented by motifs, the rooms are unit cell, and the lattice is represented by the entire building. So to identify these patterns, we must see 2D patterns first, and then we will go to 3D arrangements. So in this video, we will mostly discuss about the 2D arrangements. So to construct a pattern out of a motif, we must do some geometrical operations on that motif. So these geometrical operations are as follows, like translation. In translation, we move the motif in a certain direction to a certain distance. Like in this translation, we are moving the motif in this direction to a distance of t. In rotation, what we do is we rotate the motif around a point or an axis and repeat it after certain angle of rotation. And based on this angle of rotation, we can classify the rotational axis as 2-fold, 3-fold, 6-fold. Like in this case, the angle of rotation is 90 degree, so it is a 4-fold axis. The next geometrical operation is inversion. In inversion, the motif is inverted across a center. So the picture is... So we were talking about inversion. So when we apply inversion to a motif, the motif gets inverted across a point, and this point is called an inversion center. So here the hand is used as a motif and the hand gets inverted across this point. So the next geometrical operation is a mirror plane. So when we apply a mirror plane to a motif, we get an exact mirror reflection of that motif. Here the dog is used as a motif, and when we apply a mirror plane to the dog, we get a reflection of the dog. Now we can combine different geometrical operations and form new geometrical operations. Like here the screw is combination of rotation and translation. So here we are rotating the motif to a certain angle and we are translating it to a certain distance simultaneously. So we get a screw. Whereas in case of glide plane, it is a combination of reflection and translation. So the motif is translated to a certain distance and then it gets reflected. So we get a glide plane. So in this picture, we get a clearer picture of the different geometrical operations we were talking about. So here the motif is translated in a certain direction. Here the motif gets reflected across a mirror plane. Here the motif is translated to a certain distance and then it gets reflected. So it is a glide plane. Here the motif is rotated about 180 degree and it gets repeated. So it is a two-fold rotation. In case of three-fold rotation, the rotation is of 120 degree. In case of four-fold, it is 90 degree. In case of six-fold, it is of 60 degree. Now there are two kinds of symmetry. One is point symmetry, another one is space symmetry. So in case of point symmetry, the operations are localized in nature. So rotation, inversion and reflection are point symmetry. So if you see in rotation, we start with this motif, and after 360 degree rotation we come back to this motif, and we cannot generate any new motif by operating rotation. So the operation is localized and we cannot fill up a space by this operation. So it is a point symmetry. Whereas in case of space symmetry, it includes translation. That means we can repeat the motif indefinite number of times and we can fill up a space by these operations. So these are space symmetry. So now we will apply different geometric operation to a motif and we will see how many different distinct 2D patterns can be possible. So there are 5 distinct 2D plane lattices that can be possible by combining translation and rotation. So here we take a motif and we translate it to a certain distance in B direction, and we rotate the direction of translation and again we translate the motif to a distance of A, and the angle between these two translation direction is gamma. So based on the relationship between A, B and gamma, we can get 5 distinct type of plane 2D lattices. So here it is an oblique lattice where A is not equal to B and gamma is not equal to 90 degree. In case of rectangular lattice, it is a rectangle. So A is not equal to B and the gamma is equal to 90 degree. In case of centered rectangle, there is a motif in the center of the rectangle. So here we can take this also as a unit cell or a lattice, but it cannot be taken because the gamma is not specified here. So we take this as an lattice. In case of square lattice, A is equal to B and gamma is equal to 90 degree. In case of hexagonal lattice, A is equal to B and gamma is equal to 120 degree. So now we will combine rotation with reflection. So in case of one full rotation, we cannot generate any new motif. So we get only one motif. Now we combine mirror plane with one. So we get a horizontal mirror plane. So we get a reflection of this motif. No new operations can be generated from this. So the notation will be 1m. We will talk about notation, Hermann-Marguin notation in the next videos. So in case of 2, when we combine with a reflection, we get 2mm, not 2m, and we will discuss that in the later slide. In case of 3, we get 3m. In case of 4, we get 4mm, and for 6, we get 6mm. So there are 10 distinct point groups can be generated by combining rotation and reflection. So the answer why we get 2mm when we combine reflection with 2. So here we take a motif, that is this is a motif and this looks like E. So we apply a two-fold rotation to it. So we get a new motif here. Now we apply a mirror plane across this which contains the 2. So the rotation will be 2m. So we get a reflection of this here and we get a reflection of this here. So we get a mirror plane here. Now if you see, this is a reflection of this and this is a reflection of this. So we generate a mirror plane here. So the notation will be 2 mm and not 2m. Next, we can combine glide also. So by combining translation and rotation, we get 5 2D lattices. By combining rotation and reflection, we get 10 2D point groups. And by combining glide, we get total 17 2D space lattices. We will talk about 3D arrangements in the next videos. Thank you for watching and please subscribe to the channel.